Like it's time to start. Yeah, so we were starting to talk about coordinate descent last time. So we talked about what? Stochastic gradient descent wrap up. We talked about ADAM, acceleration. And we started briefly talking about coordinate descent at the very end. So I'll remind you what that is and start from there, basically. Okay. So what is coordinate descent? It's kind of like this. If you want to come up with a very simple algorithm that you could execute very fast, but you're not sure if it is going to do what you want it to do, then just, experiment and see. If you would do that kind of stuff, probably this is the first thing that could come to your mind. I have a function. I'll just go look at one particular coordinate and just change that coordinate. At every step, I'm changing like one coordinate. Okay. That's why this is called coordinate descent. How does it go? You pick a coordinate, and then you only compute that coordinate of your gradient, which is also the same thing as this partial derivative. And only you mess with that particular coordinate. This EIK means a vector with 0, 0, 0, only one at the spot. So basically, I'm only messing with that coordinate, and you get to pick a step size as usual. This is the coordinate descent algorithm. Why you want to do it as well? I mean, there is usually a tension between something that is rigorous and theoretically sound and something that works quick. Sometimes we find sweet spots, like things that are theoretically sound and also quick. But here the main tension is like, keep it simple, run it quick. As soon as you're quick and you demonstrate some abilities in your model, you're usually okay from a practical standpoint. Okay, that's the main motivation. You keep it simple and run it, get some results, be cool like this penguin. All right, so let's get going, but a little bit more detailed and more serious about this. So these figures are from Ryan Tibshirani and Poxos. I don't know how to read that now. We'll probably reproduce them when we write lecture notes because they're schematic, so you don't have to necessarily plot the same function. You just need to plot something convex. Okay, anyway. So first question, if I got a convex and also differentiable function, like the nicest you could think of, does this coordinate descent actually work? Okay. I don't know how long it's going to take to converge. For now, forget about the speed. Like, is it a legitimate idea to try this? Right. And the answer for that is yes. By the way, what am I doing in coordinate descent? I am at a spot X, and I can mess with any coordinate I want, and I'm not able to decrease it anymore. That's where it stops, because you pick a coordinate, you mess with it, you perturb, and then try to make it decrease. Right? That's what you do in coordinate descent. At every step, you take a multivariate complicated problem, and you just look at one coordinate where it becomes univariate and simple. Do your best, change it, keep going. Okay? And if you're not able to change any single coordinate at all, and if your function is convex and differentiable, then yes, you are at a critical point and you essentially solved your problem. And here in this picture, that point is going to be like this thing in the middle, right here in the bottom. Now, why is so? Well, if it is differentiable, literally those coordinates you're messing with are given by these partial derivatives. You're going to look at this coordinate and you're going to go this much in some direction. Right? And when you're at critical point, is the same thing as gradient being literally 0. That means all this stuff is going to be 0, 0, 0, 0. And that's when your coordinate descent will stop. It's going to look at all the coordinates, all the partial derivatives are 0. There's nothing you could change. It will just stop. And that's the same situation when you get a critical point, and if you're convex and nice, that's a local minimum. How about if it is convex but not differentiable? Let's say I have a function that is still nice. When you plot it, it is convex, as you see. Yeah. What's convex? You take 2 points, you connect the line segment. That line segment should stay above the graph, okay? If you see a convex function geometrically, this is how it looks. take any two dots you like let's say this one and that one, draw the line segment. The line segment should stay above the graph. Okay, that's how convex stuff looks like. This is convex. But suppose you're right here in your iteration. In both directions, if you're going in this direction, this is one coordinate, this is the other coordinate. The function is increasing. So your coordinate descent will not be able to do anything if you're right here. However, it's not actually the local minima. Local minima is this guy. So if you lose differentiability, you lose your guarantee. Okay? So that means you need to think about it. Maybe there is a way to fix, but it's not guaranteed. I see you're getting confused, Adam. Tell me what's confusing. Or you're thinking maybe, not confused, but maybe like trying to think something through. Very good. So what does it mean to rotate axis? It means you're allowing it to go in any direction, not only coordinates. Right? So you're right. I mean, geometrically, you see what one should do. But this coordinate thing is very coordinatized. It doesn't really see the geometry, just see numbers in the coordinates, just keeps crunching them. Yeah, actually, very good observation. Yeah, exactly. All right, so the next one is, let's say this time we got the thing coming in two pieces. Suppose this function f is a convex function that I'm not able to differentiate. However, there is a piece that is differentiable, and there's a separate piece that is just convex, not differentiable. But that separate piece, we are assuming for the specific case that it's like coming coordinate by coordinate. Okay, and I'll give you examples where this type of stuff shows up. It shows up usually, at least a prominent place where this kind of stuff shows up is like if you're dealing with networks. There's some graphical structure. Okay, we'll get there. Okay. So, however, for now, just look at it this way. There's a differentiable and convex guy right here. There's a whole bunch of convex stuff only talking to one coordinate. You're summing them through. That's why it's called separable. But you don't know if they're differentiable or not. Can I still use coordinate descent? And the answer is yes. So let's go through this. This proof is just two lines. Fy minus fx is bigger than equal to. Here, it's using convexity. This is your convex stuff right here. And here you could use convexity for g, but g was differentiable, so you can also write that gradient up inequality that every convex function satisfies. So if you remember, there were several ways to think about convex functions. I can remind you quickly some of it here. So one of them was, if my function g is convex and differentiable, then gx, gy is always bigger than equal to, we usually write it y and x the other way around. Let me write it that way as well, not to confuse you. Right? So if you go from x to y, the change in the function is always bigger than if you would go in that line segment and multiply it with the gradient. That's a way to think about convex and differentiable stuff. Hopefully you remember when we talked about this, like we were plotting convex stuff like this, right? And then here was my x, and here is my y, and I'm going in this gradient direction, and the function is always staying above. Right? That's what it means. And here, that's what it is doing. And it's combining all that stuff together, and it's saying all these things are non-negative. So that means when you're let me look at this once again. So when does your coordinate descent stop? You're not able to go any y that makes this guy smaller. You're not able to change this coordinate, you're not able to find any change for it from this function. And you're also able to not find anything here as well. And in that case, you seem to be hitting the smallest spot you could ever hit. Okay. So here is the function. So what is surprising here is like we got away by still having non-differentiability, but non-differentiable part was very specific. It was coordinate by coordinate. So in the previous example, when we lost non-differentiability, we lost the guarantee. Okay. Here, we still don't have the differentiability. Your function f as a whole, this guy right here, is not differentiable. Only this part is differentiable. But the remaining part that is not differentiable but still convex comes by coordinate. Okay, that's why you get away with it, basically. It's a very specific structure. Okay. Now, at least for this specific structure, I can use coordinate descent with a guarantee. That's for sure. And we'll try to later think about stuff where you can even do it with more general convex and non-differentiable stuff. But for the moment, this is good enough. Okay. All right. Now, let me give you some examples that might look like this. So here is what's called empirical risk minimization example, a typical situation. You got your measurements, AJ matrices, or you could think about all those AJs as a matrix A, and AJ is like the jth row of that matrix. Suppose you're doing something like linear or logistic regression, right? And then you'll multiply that row with your X, and then you got some loss on top, and you're summing it up. And then here, sometimes you got some regularization term, like L1 norm, L2 norm. We put that stuff on our models before. And why it is called empirical? Because I'm usually using only this number of data points here, and it's empirical. I just sampled them. I'm not looking through all possible data right there. Okay. And using this, we are going to run some optimization scheme. We are going to try to fit the best A we could. That's going to be our linear model, for example. Okay. And in that case, it kind of fits into this framework as soon as this part is differentiable. This part can be just convex since it is coming like data by data or dot by dot, coordinate by coordinate. This part, you need differentiability. Okay. For now, what I was saying here, I was saying, even if GI is not differentiable, your stuff works. But for now, suppose look at the differentiable case and try to take the gradients and see how they look. At the end, we are going to do a coordinate descent by taking a step size and looking at that coordinate of the gradient vector and then going, that much. So let's look at how the gradient is looking. So gradient of Fj on AJX comes out as AJ being linear. Apparently it comes out. And then you just look at the gradient of this function F. Okay. So what's going on here is like, think about, you have a function F, inside you're putting A times X. And how would chain rule come out? Gradient of that function inside A times X, and then times A times X derivative, which is A. Okay, that's basically what's going on. There is nothing fancy. So ith coordinate is easy to compute. It just comes out this way, turns out. So you compute that through all those stuff in the summation. And since on the right-hand side, only one of them was dealing with that particular coordinate, you only care about that, ignore the rest. And this will how your coordinate descent will start looking like. If this is not differentiable, you can still do a little, trying to tweak in any direction you want and get away with it, as we saw in the previous discussion. Okay, that's like a typical situation. Empirical risk minimization is almost always what you do when you're training a machine learning model. So you take your loss through your data, optimize, change your parameters, take another data, do the same, keep going. That's what we do all the time. Okay. So in many cases, your training process could fit in this coordinate descent framework, even though the coordinate descent looks such, heuristic, simplistic idea. It still is not too bad. Okay. All right. Okay. Let me give you some more examples here. Apparently, I'm also thinking when I was writing the notes that the computational cost is also likely not too bad. Because you're just computing derivative of one of those functions for every coordinate, and the other one just looking at a particular part of that gradient vector. Okay. Another example that is also common. Suppose you got some measurements, you got some data, like you have some sensor data about, I don't know, ships, airplanes, wherever they are, but it's noisy. However, you do not know how much is the noise. Okay. You would like to estimate variance in that database. And let's take it to the simple case. Let's say I know my stuff is Gaussian. Suppose that's what I believe in. And then I sample a whole bunch of data. I would like to understand what is that covariance matrix. Okay, that's my goal. I'm trying to fit a probabilistic model. I got my measurements from whatever application you're measuring from, and you'd like to fit the best Gaussian you could. This is called covariance estimation, a pretty standard problem. Here's how that goes. You take the logarithm of the likelihood function. So if you remember, we talked about maximum likelihood estimation, right? So if I assume this covariance is my prior, you compute the posterior, right? And you look at how that probability looks like. What you're trying to do is like you're going to try to find the sigma that maximizes what you have seen by sampling in terms of probability. So if you fix the sigma, you solve these and you can compute what was the probability of getting that. What was the probability of getting that, right? If you fix the sigma. What you're trying to do is like find the sigma. When I fix it, the probability I get out for what I actually have seen is maximized. It's kind of like fitting the data you have observed in a probabilistic way, okay? That's maximum likelihood estimation. So we are going to do maximum likelihood estimation here to find the best covariance matrix. And when you write down, it comes out something like this. Logarithm of determinant of square root of that guy, something like that. And then some constant numbers. And then here is where data and the covariance actually interacts. You look at that vector, you look at the inverse of the covariance matrix, and you multiply it with the vector once again. Now, don't forget, this is a number now. Matrix, left and right vectors, this is a number, okay? And we are trying to find the sigma that maximize the sum of those numbers through my data. That's what the maximum likelihood estimation corresponds to. So far, is everyone following what the problem is? I could wait and explain again. Yeah. So we want it to be big, I'm sorry. When you do minus, you want it to be small. Usually, you're right. So when people usually write it with a minus, then you want to minimize. For now, I'm trying to maximize. Okay? I want to have the maximum probability assigned by my choice of sigma to what I actually have seen. Does that make sense? So if I did the math right, which we have to check, for now I should be maximizing, and maximization will probably have a trade-off, like something big here, something small here, we have to check, okay? Let me go through the math and we'll fix a mistake if there is a minus plus one. There could be a mistake I did somewhere, let's see. Looks like and maybe the next line is already kind of answering, so people usually put a minus in front. If you're trying to maximize something, it's the same thing as minimizing the minus. And this would be called negative likelihood. So if you're doing negative likelihood, you're minimizing. If you're doing positive, you're maximizing. So if you look at this way, then you will be minimizing. What are we minimizing? This thing here, minus in front. I think this is going to be now a plus 2. Yeah, this is the one, there's a mistake. Okay, let's go slow. So logarithm of determinant of minus square root. This will give me a minus outside, and then there will be another minus. I think this should be a plus. Okay. Now, when I do negative likelihood, things start looking nicer. I'm trying to literally minimize this. And this is... No, apparently I was right. Sorry. Now I figured. Because apparently I say, okay, let me keep it easier. Let me give this guy's inverse a name. Let's write it in this way. Okay, I'm minimizing this function. And now let's try to stare at that function and see if that would fit into our framework. Next step, I'm trying to write this, trying to incorporate all data points at once. This was for one data point. Think about like one data point being a column of a matrix. Try to think about your data like a big matrix, okay? If you try to write it that way, it also comes out as like the summation of those. You could write it as X transpose X for that data matrix. Inner product with this matrix theta. And that inner product is the matrix inner product we have been using. So trace inner product. We had inner products on matrices. Hopefully you remember. A inner product P was what? Trace of B transpose A, right? So you can write it in this matrix language too. And that's our objective function. You could also put some regularization. You don't want your matrix to go crazy. You say, let me add a regularization term so that the norm of that matrix I'm trying to fit the covariance matrix is also controlled. Okay. So that could be a norm. And we usually actually wish not for that square, Frobenius or trace, whatever norm. This is literally taking entries, squaring them like Euclidean. This is what it is. We usually don't want it. We usually would like actually something like L1 norm. So let me remind you what these were. Let me remind you in the case of a vector, matrix analogy is somewhat straightforward. So what is this two norms talking about? If I have a vector, say alpha, two norm is the standard Euclidean norm we know. One norm is summation of absolute value of the coordinates. What is the difference? L1 norm cares about sparsity. L2 norm only cares about the magnitude. How big is it? And when you're fitting a model, when you're looking at your covariance matrix, what does it mean for that matrix to be sparse or not? What is the meaning of covariance matrix? So you write down the covariance and you see like first entry, 1, 1, second entry. So what is this? These are relations between the coordinates of your randomness, right? Right? So sparse means you're assuming coordinates are like more independent than each other. That's what sparse model means. If it is not sparse, every coordinate has a relationship with the other. Computing with it will get complicated. The more independent your model is, the easier it to work with that. Okay. So here you would usually prefer L1 because you would like to fit a covariance matrix, which does not say every coordinate is related with the other. It will pick the coordinate relations for you. Okay. So this way you will also see kind of like which group of features are related to each other, which are seemingly independent. If a group, say you got like 10 features, they're extremely correlated. If you like, then you can subsample. Just use few of those because they're extremely correlated. You don't have to use all of those. Yes, you had a question? Regularize means the following. This was your objective. You're now adding a term to it to put some regularization on the object you're going to get out of it. Without regularization, it's going to go try to solve this optimization problem, and theta could be whatever satisfying, minimizing this one. So this one will keep it not so big because you're trying to minimize this added next to it, right? So if it is too big, this is going to be a huge number. Your gains from here will be killed, so you're not going to be doing minimization. Regularization is this idea. You have an objective function. You would like to regularize whatever parameters you're getting out of it, and then you get to decide how do you regularize it. Yeah. So this way, you will only regularize how big is that, and this way, you're also caring about the sparsity. Okay. When you actually use packages, here you will also have a term, a number, I'm sorry. And this would be the regularization rate or regularization constant. So let's say if you pull up a package, PyTorch, it will allow you to mess with this number. If you make this bigger, you're regularizing aggressively. If you make this number smaller, you'll regularize more modestly. Okay? You could also get to pick how much I do care about that regularization. Yeah. For example, this like maybe 5 days ago, I forgot the day now. I was running a L1 regularized objective to pick out something sparse, but a priori, I have no idea what lambda is the best thing there. So what do? You pick a range for possible lambdas you have in mind. You keep training and testing your model through a whole bunch of different data. And whichever one has the least test error, you're like, okay, probably that's a good regularization parameter to pick. Okay. So unless you know a lot about your application, it's really usually hard to know regularization exactly what should it be. We usually go by empirical experimental ways to pick out. Okay. Anyway, the punchline is when you look at this guy, hopefully this also fits to your coordinate descent perspective. So this determines stuff for positive semi-definite matrices. Surprisingly, it's convex and differentiable. It looks complicated, but it turns out to be a nice function. This guy is okay. And here, what do I get? I'm getting like data matrix multiplied with my matrix. This is again, actually, even this one is differentiable. The only issue comes in when you regularize, L1 norm is not differentiable. L2 would be still differentiable. Okay. But when you look at the L1 norm, now you need to ask me like the convex guy in our framework, which is not differentiable, was, where is that? Right here. It was separable. Every convex piece was talking to only one coordinate, right? So how on earth this like L1 norm is doing the same? Well, when you look at the definition of L1 norm, you see L1 norm is also coordinate by coordinate. So even though it's not differentiable, it still fits in our coordinate descent perspective. Okay. All right. So that's another example. One other example is, by the way, when you regularize with L1, like we are doing now, the buzzword for it is to call it lasso. I don't know why it's called lasso. Well, actually, I know, I lied without intention. It's a short for this long thing. I don't know why they come up with that long thing. Least absolute shrinkage, blah, blah operator. Okay, so that only means your objective function is regularized with L1, nothing else. Yeah. So when people say we did lasso, that's what they mean. Right. So we have been talking about lasso already, basically. Okay, so now here's what's called graphical lasso. What does that mean? So I got like some sort of network-like application. You know, let's say you're on Facebook on your phone, you're part of this network, right? Okay. And then you would like to, off of your data, you would like to understand the network. You don't know everything about the network. You have pieces and bits of information about relationship between different nodes, and you like to come up with your best fit. This type of stuff usually fits into this coordinate descent framework. Why? It usually comes out like this. You got two nodes, xi, xj, and you got some function about the strength of the weight between them. Are they like really connected, weakly connected? And this stuff should usually come out as differentiable unless your weights are crazy. Okay. And usually people also have some weights on the nodes. You have some idea that some node is more impactful than the other. And you put objective function as such. And now it's going node by node. So it's like coordinate by coordinate. And that G stuff could be just convex. It will fit into this coordinate descent framework. Okay. So for graphical type applications, since it fits, I think it's usually implemented, probably in scikit-learn, for example, graphical lasso is already implemented. And it will usually default to coordinate descent. Because normally you could take this objective function, then you could go pick your optimizer. You could try to fit your best with whatever optimizer you like. You could go pick Adam, whatever, right? So since it kind of directly fits to coordinate descent, unless you change it, this kind of stuff would be already usually defaulted to coordinate descent already. And the good thing about it is, like, if it wouldn't be coordinate descent, you may not know this. If this is like some sort of L1, maybe you will not converge because it's not differentiable. Standard gradient descent may not work very well. Okay, very good. And here, what am I doing? Let me see. Yes, so I'm gonna now give you a theorem about this. Before the theorem, any questions about examples fitting to this framework? Could you say it again? So there's like two main lines. One is, so within this course, this fits directly, so we talked about it, and I can give you pointers for this particular thing, graphical lasso. In general, if you're working with graphs, so it used to be called network science for some time. And I didn't know this, I learned it maybe last year, I don't know. So apparently in 2000, maybe 10, US Army designates network science as like a very critical direction. So they put a lot of money, and there comes a whole bunch of papers, so that made network science somewhere between science and pseudoscience. So there's so many papers, it gets hard to navigate. Okay, the Python library for this is NetworkX. It's got common things implemented there already. And nowadays there is also growing literature on what's called graph neural nets. You probably heard about it. It's just bargaining yet. It's not so well established. We still don't know how to really do graph neural nets. I'm not an expert on this. That's what experts told me. I'm kind of parroting now. The main issue seems to be like a lot of our machine learning stuff needs a vector. So you need to take an entire network, turn it into a vector. And how do you do that is the main tricky part. That's one direction. There is the second direction, which existed in optimization community earlier, now also getting into machine learning, called graph embeddings. So we talked about word embeddings or token embeddings, right? So when we were doing recurrent neural nets, you got like a word, you take that word into like a super high dimensional space, it becomes a vector. The point is two words that has a similar meaning should be close vectors after you do this. That's word embedding. They try to do the same with graphs. You use this embedding idea to get the vector, basically. Then after you do the embedding right, you could feed it into whatever machine learning scheme you already have. As soon as you have a vector, you have entire machine learning under your belt. So this is what I could quickly say. And within optimization, this graph embedding idea existed before. And the one particular technique within convex optimization is called semi-definite programming. It kind of fits into this. If anyone is interested, we can talk sometime. Okay. All right, let me now give you a theorem about coordinate descent. Like, we have guarantees for this thing in certain cases. Let me talk to you about it. Suppose to be able to prove something mathematically, we are going to assume some niceness on our functions. So for now, we got a convex and differentiable function f. All right. And then this is like the minimum set. The minimizer doesn't have to be unique. There is like a set, right? And then this is where I start my iteration. I just started x naught. And think about all such x's that when you put it in, it's smaller than where you started. It's going to be a lot of points right there. And these are the points where you want to find the minimizers. So one thing we need to assume is like where I start is not too far from this set, or at least I have an idea how far is it. It could be a little further out, but I have some idea how much far away I'm starting my iteration. That's the first thing. This is called R0. Right? And then I'm going to look at the coordinates of my f, right? I'm going to take the gradient, look at the coordinates of the gradient, and iterate. That's what coordinate descent is going to do. So we would like to assume those coordinates are not crazy. Like if a partial derivative is changing so much with just a little tweak, things can get kind of unstable. So our assumption here is like, if I'm at a point X, I'm looking at the coordinate 5, say, and at that coordinate 5, I'm perturbing this much, t. The change could be at most a number times that t. Okay? That's what you're assuming. It's a Lipschitz assumption, basically. And every coordinate could have a different Lipschitz number. For example, first coordinate could be more sensitive than the fifth. In the theorem I'm going to give you, we are going to go by the worst coordinate, the maximum Lipschitz. There's a more refined version which takes into account all those Lipschitz as well. Okay, so to keep something a bit more simple and easy to state, let's go by, suppose all those Lipschitz is like some big L. Yeah, all right. And then the theorem goes like this. At each step, I'm going to pick a coordinate uniformly randomly. And then I'll do this fixed step size with that big Lipschitz constant L. And I'm going to run my coordinate descent. Okay. Since I'm picking coordinates uniformly randomly, the guarantee you will get will be probabilistic because you're picking coordinates randomly. Okay. So here the assumption is like, I don't necessarily know which coordinate is better to mess with. Since I have no idea, I'm picking something randomly. Okay. All right. And then I iterate the algorithm k times. In expectation, the error cut would be linear in terms of the number of steps. This is the bound on how far you could be when you start the iteration. This is the definition. This is that Lipschitz constant. This is that number of steps. Okay. And this is the number of coordinates. In the other stuff, when we were not doing coordinates, gradient or stochastic, we did not have that n. Okay. So here I'm literally doing just one coordinate, and you should think, hopefully, the number of steps is much bigger than the number of coordinates, so that this gives you anything reasonable. Okay. So the reason that n popping up there is basically you're thinking, I'm picking a coordinate randomly. What do I expect? Well, if this is like the best coordinate to mess up with, lots of gains, but it could be also the worst. So on average, you get like that n term. It's like the great loss divided by n popping up, basically. Okay. Right. That's the guarantee we have. And if we have even more about your function, if it is like strongly convex, it's not, this is convex. If you have a little more, then it's strongly convex. And in that case, you could prove stronger guarantees. Okay. All right. Now, timing is not bad. So let me kind of walk you through the proof. The proof itself is not the main point. Trying to see why this works is the main point. Okay. I'm not going to ask you to reproduce the proof. However, the reason I'm going to go through it is like you will see this is actually not a magic thing. Okay. So let's say if I pick the first coordinate, this is how my iteration is going to look like. Take the gradient, look at the first coordinate, mess with your stuff in that direction, in that coordinate, I'm sorry. Okay. Okay, then what do? I do our standard tricks. We have this descent lemma when the function is smooth and L smooth, whatnot. At every coordinate, this guy is L smooth. That's what we are assuming. At every coordinate, the gradient has that Lipschitz satisfying. Okay, so since it's correct in every single coordinate, I can apply it for this particular coordinate. So just write down those stuff we wrote in analyzing gradient descent or stochastic gradient descent, and you will get something like this. Okay. And then, in other words, fk minus fxk is less than minus this. So that means I am gaining at least this much at every step. Okay. So how much I'm gaining? I pick that coordinate of that partial derivative. Kind of square of it is what I'm gaining, more or less. Okay. And now, depending on how big is those, that's your gain. There is where you do that averaging stuff. How big is a coordinate of a vector on average? Take the whole norm of the vector, divide it by n, right? That's like an average norm of a coordinate. And that's where this n comes up. And that's why you end up getting like the n in the estimate back. It's basically following through what we have been doing. There is no much of a change. Okay, that's what I'm trying to say. This is how we analyze gradient descent, how we analyze stochastic gradient descent. We just look how much gain is happening. It's usually going to be controlled by the norm of that gradient. In this case, only that particular coordinate of the norm of the gradient. And since I'm picking coordinates randomly, I'm able to say the worst case scenario is going to be norm divided by n, and then it pops up. Right? Okay, this is a theorem for coordinate descent. I work it out step by step in the notes. We don't need to go through all of that. So a more refined version would be caring about all that Lipschitz constants, not only fixating on the maximum. You would go like sum up those Lipschitz, and picking the ith coordinate will be this probability. So I'm kind of prioritizing coordinates with respect to how sensitive are they. That's a different way of uniformly picking a coordinate, not uniformly, probabilistically picking a coordinate. And if you're going coordinate by coordinate, you could adjust your step size that way too. If I'm at coordinate 5, and if that guy is super sensitive, decrease your step size. If it is not so sensitive, increase it. So you don't have to fix the step size. You can change it depending on your coordinates. And if you do that, you run through same analysis, you end up getting, instead of that n, something like this. Summation of all the Lipschitz constants. So here in the other analysis, we got the biggest one times n. In this one, you got summation of them. Of course, biggest one, n times is bigger than this quantity. So you get a little better, but more or less in the same spirit, I would say. Okay. And of course, Nesterov, having his accelerated stuff, when he sees this, he also gets here and accelerates coordinate descent. As you could imagine, he tries to mess with all the parameters and tries to find the best ones to get it faster. And that apparently turns out to be this particular choice. Right. I worked through this, but now I forget. It's basically you go back to Nesterov accelerated gradient descent, which is somewhat of a mystery, as we discussed. You apply the same techniques in this particular situation, and that's how the optimal randomization comes about. Did I wrote? Yeah. And then his guarantee is this. So he goes from summation of them to root squared, but this is the main gain. He manages to, again, change that number of steps to squared. It's much quicker convergence. Okay, I think that should be the end of coordinate descent. I'll start something else now, but before I do, any questions about this one? So this surprisingly simple thing still admits certain theoretical guarantees. Yeah, that's the interesting part, and it's easy to implement. And that usually is the default algorithm for many packages. Okay, let me stop the recording and start it again because we are switching topics. I'll split the video.